Okay, so my name is Connor Tullock. I'm a solutions engineer here, and I wanted to quickly run through the AEC vertical data stack and how it fits in with the engineering industry, and more importantly, what the scalable API-based tool might look like in practice to give our clients a way to bulk download the engineering data set that they would be interested in using. So I have this right up here, and just to quickly define what the goal of the backend Python script is, it's to allow our customers to download this data stack. So get access to an offline version of high-resolution imagery, terrain data, and a planimetric base map that's derived from our AI attributes. The reason that this is important is because it's the basic building blocks that an engineering client needs to begin some concept planning and early preliminary design. And again, we can give access to this data set very quickly and efficiently using our APIs. So what I'm going to do now is kind of just explain what that workflow looks like. In practice, we would either have a front-facing client web portal to manage these downloads, or we would assist on the back end to provide this processing script, and then they could use a GIS application as a front end. So what the workflow looks like is a project manager at a large-scale engineering company wants to make a request for data as a new engineering contract comes up, right? So what they do is they write that request. They need the ability to define their area of interest that they want data for. And then from there, we send requests to our Tile API, our DSM, DTM API, and then our AI API, package it up neatly for them, and then deliver that package for use on their local machine. So I'm going to quickly just pull up the example Python script here. What I have written is this standalone data pack downloader Python script. And what it does is it gives the user the ability to input 3 different values currently. So they need to provide an API key. They have to provide a area of interest that they are looking for data on, and they have the ability to provide that in either a KML file or a GeoJSON file. And then the third user input is defining where they want their files to be saved on their local machine. Down the line, building in additional functionality to define more user input for things like capture date, as well as what AI packs they want to download, I think is really important, but that is not currently built into the workflow. So let's run this on our local machine here. So what you're going to see is this first input will pop up after the script runs, asking for an API key. Enter your API key. Then it's going to ask for a file input. So I have this pre-made GeoJSON ready to go. And then it wants an output location, so I'm just going to pick the exact same location as the script is saved. And I will pick AI features. Actually, I'll just pick data set. Alright, so then the script is going to run. It takes a few minutes to go through and pull the data. Again, what you're going to receive is most of the data download is managed through a grid system because of the API size restrictions. So in both the case of the static imagery, the DSM requests, and the AI data requests, what the script does is it takes the user shape area of interest that they want. It defines a grid system that covers the shape, and then it goes grid by grid to make queries on the intersection shape between the original AOI and that grid to get a more refined data set for every grid location. Again, down the line, an additional processing step that needs to get built in is a way to take those grid responses and stitch the imagery and the DSMs together. In terms of the AI API request, what actually happens is it makes a payload request in that grid system, and then it uses a variety of ArcGIS toolboxes, the ArcPy toolboxes, to take the response and merge all of the data layers to remove those grid lines. There's a little bit of cleanup as well, in addition to just those grid line cleanups. And then there's an additional toolbox that gets run that converts the ArcGIS line work into CAD line work, which is a much more usable format for engineering clients. So I'm going to jump ahead and just kind of talk about what the payload looks like now. So going to my folder here, I actually ran this on a different data set right here, which is this version 2. So what you can see here is the first data response are these TIFF images. So the TIFF images are the simple static image responses from the Tile API. The second output is all of the raw AI data responses, as well as this DGN CAD drawing file. And then the third response is the DSM grid, which is actually giving you that 3D surface information. So I have those pulled up in ArcGIS. I'm going to just toggle through them quickly. So for the project location here is in Hartford, Connecticut. I have the image base map right here, which are those tile responses. The raw AI API output is right here, which gives you a good picture of what that original query shape looked like. And as you can see the grid lines that come in as you make those requests across. So overlaying that out with the imagery, you can see the grid responses here. And then finally that DSM 3D data response. It takes a second to load in here. And then finally that DGN drawing. So ArcGIS is able to load these DGNs. So the assumption though is that this is going to be loaded within a CAD environment and actually used as that planimetric base map that is so important to have access to. So that kind of sums up what that workflow looks like. And again, the intention here is to provide a solution for scalable access to data for engineering firms that are covering the whole country, and what they're trying to do is get as comprehensive of a data set as possible, as quickly as possible for these jobs, so that they can start design that day, start making decisions on if they want to go after a job or not, rather than spending their time trying to search around to acquire data that is going to let them make those design decisions.